Hello, I'd like to present our recent project on minimizing communication while maximizing performance in multi-agent reinforcement learning. This is joint work with Hissam Sheikh, Somdev Majumdar, and Mariano Philippe at Intel Labs. Multi-agent reinforcement learning can be used to train agents that work together to solve a common goal. For example, we could train a team of agents to play a game of soccer or jointly explore an unseen area. In many situations, our agents would perform much better if they could communicate with each other. This would allow them to share information and agree on global strategies. In a navigation task, for instance, agents could send messages about regions they had explored. However, in practical applications, communication is an expensive resource due to bandwidth restrictions and network costs. Therefore, we would like our agents to use the communication channel judiciously. In this work, we try to achieve good task performance while minimizing the number of messages sent. We now present the gated communication framework that we use to solve multi-agent tasks with efficient communication. At each time step, our agents generate messages M and binary gate C. If the gate C is turned on, the message will be transmitted to the other agents, otherwise it will be dropped. In the diagram on the left, for instance, we see that agents 1 and 2 transmit messages, while agents 3 and 4 do not. The agents are parameterized by a set of neural network modules. First, the aggregation module processes incoming messages into a single vector X. Second, the encoder module combines the vector X with the local observation O and past hidden states to produce a new hidden state H. From this hidden state, the message generating module, the gating module, and the action module read out the messages, gates, and actions respectively. We experiment with two message generation and aggregation methods, COMNET and Tarmac. In order to optimize the binary gates, we use either the Gumbel softmax reparameterization or the reinforce algorithm. In each case, we modify our objective function to minimize communication alongside the standard RL term to increase task performance. With Gumbel softmax, we do this by adding the sum of the gates, weighted by a hyperparameter. Due to the reparameterization, they can be minimized by backpropagation. With reinforce, we treat the gates as additional actions and modify the RL rewards to account for communication cost. We test our methods in 3 environments. The first environment, secret, consists of 5 agents. The agents need to guess a secret that is fixed for the duration of the episode and is only given to the first agent. Therefore, the agents must learn to share the secret. The second environment, predator-prey, is a navigation task with partial visibility. In order to succeed, all agents must reach a target location. The third environment is secret pairs. The agents are divided into pairs, and in each pair, only one agent knows the secret. Here we try to learn gating decisions for each receiver. In secret, we see that ECNet greatly reduces communication with a small cost to task performance. The communication penalty is essential to achieving this reduction. IC3net, which includes gating but has no communication cost, cannot decrease the number of messages very much. In predator-prey again, ECNet is able to retain task performance while decreasing communication cost. Further, we find that it is possible to obtain different trade-offs between task reward and communication by further increasing the penalty. In secret pairs, we find that our algorithm is able to obtain the correct pattern of communication. Messages are only sent by the agents that know a secret and only to the corresponding receiver. We note that it was necessary to supply the pair ID as an input. To conclude, we have shown that it is possible to increase the efficiency of communication in multi-agent RL with a simple modification to the objective function that accounts for communication cost. For additional experiments, please refer to our paper in arXiv. Thank you.